Good day to all. Today we can discuss about the PLL applications in the subject linear integrated circuits. The output from the PLL is generally obtained as a voltage signal or as the frequency signal at VCO output terminal. So the voltage output is used in frequency discriminator applications, whereas the frequency output is used in frequency synthesis or clock recovery applications. So this is the way based on the output, the PLL applications can be vary. So because whenever all these conditions has to be satisfied, the PLL has to be made to lock. So mainly, whenever we are going for frequency cases, the output will be having a corrupted with noise and other disturbances. So the PLL has to be made to lock selectively on one particular frequency component at the input. Some of the typical applications of PLL are frequency multiplication or division, frequency translation or frequency shifting, AM detection, FM demodulation, FSK demodulation. First one is frequency multiplication or division. So it is having the normal PLL block diagram along with the divide by n network. It is nothing but a counter. So here the one which is highlighted is represents this PLL, and this will be a frequency divider network. So the counter value will be deciding the factor of this n value. So n should be carefully decided as well as the divide by network inserted between the VCO output and the phase comparator input. So the what about their output should be the VCO output is F naught equal to N into Fs. So multiplication factor can be obtained by selecting a proper scaling factor N of the counter. So it is actually the input signal is based on example square wave or pulse train we are using, then the VCO can be directly locked to the harmonic of the input signal with the corresponding to the nth value. Okay. So, however, the amplitude of the higher order, if you are increasing the n value, the effective locking may not be taking place. So that you have to keep the n value lesser than or equal to 10 for your typical applications. So it is also used in frequency division. Since the VCO output is rich in harmonics, it is possible to lock in the nth harmonic of the VCO output. F naught equal to Fs by F. So the output is nothing but we are going to divide that by the input frequency. Second one is frequency translation, or we can say it is the frequency shifting. So it is also having the normal PLL block diagram along with the multiplier and the low pass filter. So this whenever the what is multiplied is the VCO output is multiplied. This VCO output is if you are multiplying, we will be getting two signals. One in the plus or minus Fs, another one should be F naught minus Fs, because always multiplying two signals will give a positive component as well as a negative component frequency. And but you are having a low pass filter which filters or allow only the low frequency component. So the difference in component F naught minus Fs is allowed to the phase comparator. And what is the input to the phase comparator is, instead of VCO frequency, it is having another one offset frequency F1. So what should be this F1? F1 is nothing but comparing the F naught minus Fs. So what is your F naught? Fs plus F1. Thus it is possible to shift the incoming frequency Fs by F1. So the translation or offset frequency is applied to the comparator. When PLL is in lock state, you will be obtaining, you will be able to shift the incoming frequency Fs by F1. And the next is AM detection. So AM input will be given as input to the phase shift 90 degree, and VCO output already it will be having a phase shift of 90 degree. So what happens is the AM input is shifted by 90 degree and the VCO output is shifted by 90 degree means your output signal obtained will be in phase now. There will be no phase difference. The PLL is locked to the carrier frequency of the incoming ASV. So whatever the carrier frequency of the incoming signal, that value should be locked. That is the lock-in frequency. The output of the VCO, which has the same frequency as the carrier, but unmodulated, is fed to the multiplier. So both the phase will be compensated whenever it is shifted by AM input is shifted by 90 degree. So now the output of the multiplier is in the same phase. The output of the multiplier contains both the sum and difference signals. So the low pass filter will allow only the low frequency component, that is your message signal frequency, which will be equivalent to the message signal frequency. Since the PLL is tracked to have the same as the carrier frequency as that of the VC output, so you will be getting a same demodulated output frequency. Next is FM demodulation. So if the PLL is locked to the FM signal, the VCO tracks the instantaneous wave, the same block diagram. There is no change in the block diagram from the PLL. So the filtered error voltage which controls the VCO and maintains lock with the input signal is the demodulated FM output. So VCO is used in all linear FM demodulators. Next is frequency shifting demodulation, that is FSK demodulator. So as you know, FM demodulation we are using here also we can use in this FSK demodulation. The block along with this block diagram is shown with an operational amplifier. So here the binary data can be retrieved using a FSK demodulator at the receiving end. The I565 PLL is very useful as a frequency FSK demodulator. So this FSK demodulator using PLL for this is one of the application for tele-typewriter signals of 1070 Hz and 1270 Hz. As the signal appears at the input, the loop locks to the input frequency and tracks it between the two frequencies with the corresponding DC shift at the output. So there are three stage filters, RC, RC, RC. It is a three-stage filter which removes the carrier component and the output signal is made logic compatible by the voltage comparator. So the last one should be the comparator, and in between there is a three-stage filter. The first one should be the PLL. So along with the PLL, we can able to demodulate the output signal at the frequency of 150 Hz. So 1070 minus 1270 is the frequency FSK input it is used. And this 600 ohm is for matching the impedance it will be used. So likewise, we can use this PLL in various applications. We have seen 5 different applications. First one is frequency multiplication or division. And the second one is frequency translation. Third one is FM demodulation. Fourth one is FSK demodulator. And apart from that, AM detection. So 5 applications we have seen. This is, hope you have understand this. Thank you.